For number 18, we have another voltaic or galvanic cell, and they want us to pick what's true. And so before we look at any of the answer choices, let's just figure out what's going on. So let's think about which is being oxidized and which is being reduced. And so first we'll start by figuring out what's being reduced. So we have aluminum ions, and we have gold ions, and we can write their reductions, and then pull the potentials for each from the table. So we can see that aluminum has a reduction potential of negative 1.66 volts, whereas gold has a reduction potential of positive 1.69 volts. So gold is more favorably reduced, so this will serve as our cathode. And we'll instead say our aluminum metal must be being oxidized, and we can flip our reaction. So when I rewrite the equation, I also rewrite the potential. So now it's talking about the oxidation of the metal rather than the reduction of the ions. And then I can add these together to get my overall cell potential under standard conditions to be 3.35 volts. Okay, but if I wanted to combine these two equations to add them together, I would need to adjust them a little bit to make sure that my electrons would cancel. And to do that, I need to write a 3 in front of the bottom reaction so that our 3 electrons would cancel. And our new overall reaction would be 3 gold ions reacting with aluminum metal to produce 3 gold solids and aluminum ions. Okay, so as we said, the gold side is going to be our cathode. The aluminum side is going to be our anode. So the aluminum is giving up electrons in the oxidation reaction. So electrons are going to flow through there to the gold and reduce the gold ions. And when that happens, some solid gold is going to form on the electrode. Whereas on the aluminum side, it's kind of dissolving. So some aluminum ions are going into solution, and we'll sort of have a hole in our electrode that's formed. Okay, and then since the anode is losing electrons, it's sort of becoming more positive. So we'll have anions from the salt bridge flow down to balance the charge. We'll have some cations flow toward the cathode to neutralize that added negative charge from the electrons. So now that we have a picture of what's going on, we can figure out which is true. So in answer choice A, they say aluminum ions are reduced at the cathode. That's false. The concentration of gold ions will increase over time. That's false because we're using up those gold ions to make more gold solid. C, the mass of the aluminum electrode increases over time. That's false. We're sort of dissolving it and making more aluminum ions. So it would actually get lighter. D, the standard cell potential is 0.03 volts. That's false. Then E, electrons flow from the aluminum to the gold, and that is true. So I do really like to map out what's going on before I even look at the answer choices, so I'm not tempted to change my picture to fit the options. Okay, in number 19, they want us to figure out which is the best reducing agent. And so we know that a reducing agent gets oxidized, so it loses electrons to become more positive. So with the aluminum here, you can think about aluminum losing some electrons to become something like Al3+. With lithium, if it lost an electron, it would become lithium 2+. With Cl2, we'd probably have something like Cl+ if it lost electrons. With zinc, we might have something like Zn2+. And with fluoride, we would maybe just make neutral fluorine. Okay. So now we can look on the table to see if we have potentials for these reactions. And so for the aluminum reaction, we'll have that positive 1.66 volts. And then if we look for a lithium and lithium 2+ reaction, we'll see that it doesn't exist. Lithium isn't going to lose, lithium ions won't lose another electron to become lithium 2+. As lithium plus, it already has its noble gas configuration, and it's not going to lose another electron to go beyond that. And the same is sort of true for the chlorine. We're not going to make positively charged chlorine. Chlorine needs to gain an electron to reach its noble gas configuration, which is why we oftentimes see it as Cl-. We're never going to see it as Cl+. And there wouldn't be any kind of reaction like that on the data sheet. And then we can look for the zinc reaction and the fluorine reactions potentials. And then we can compare, well, which one's the most positive, because that would be the one that's best at being oxidized and the best reducing agent. And that's going to be A. And so another way to approach this is to look for these compounds on the product side of the reduction table. And if they're on the product side, then you can look for their potentials. But I like to just think about what they would become if they were being oxidized, because sometimes it doesn't make sense and you can rule things out. In number 20, they give us concentrations of silver ions and lead ions. They want us to figure out which will precipitate first when we add in bromide through sodium bromide. And they give us the KSP for the different salts. And so I know that for this first salt, my KSP is going to be equal to my silver ion concentration times the bromide ion concentration. And so I know my silver ion concentration because they give it to me in the problem. And it's going to be that 2 times 10 to the negative 4th molar. And if I solve for the bromide ion concentration, what I'm really solving for is the maximum amount of bromide that I can add before a precipitate forms. And as soon as I add even a drop more, I'll start getting solid. And so I can solve for the bromide concentration for both of these, and whichever number smallest is saying I need less bromide to be added to get my solid to precipitate. And that's the one that would precipitate first, so it requires less bromide to be around, so less added in. And so we can use the KSP from up above to solve for the bromide ion concentration. And for this one, it would be 3.85 times 10 to the negative 9th molar. So as soon as we add even 4 times 10 to the negative 9th molar, we'll start getting some silver bromide precipitated. And we can use the same logic for this lead bromide. We'll have a different KSP expression. It's going to be our lead ion concentration times our bromide ion concentration squared. We know our lead ion concentration from up above is 1.5 times 10 to the negative 3 molar. And then we can solve for bromide using the KSP above. And we get that our bromide ion concentration is 6.63 times 10 to the minus 2 molar. So we would have to add a lot less bromide, like 10 million times less bromide, to form silver bromide solid than we would have to add to form lead bromide solid. And so the AgBr is going to precipitate first. In number 21, they want us to figure out the measured cell potential of this reaction given some different concentrations and the standard potential. Since the concentrations aren't 1 molar, we're not at standard conditions, so we can't just use the standard cell. And we'll have to use this full equation. And so they've already done a lot of the work for us, because we see that our standard cell potential is 0.78 volts. So of that minus 0.0592 divided by our number of electrons transferred. And so we can figure this out by looking at how the charges change. We go from 2 plus to 0, and 0 to 2 plus. So our number of electrons transferred is just going to be 2. And we'll have that times the log of Q. So we'll have to figure out what Q is. So our formula for Q is going to be our aqueous products, so their coefficients, divided by our aqueous reactants to the power of their coefficients. So here we'll just have 0.01 divided by 3, which I'm going to write as 3.33 times 10 to the minus 3. And you can plug that in for Q. And when we solve this, we'll get our answer, which is 0.853 volts, which corresponds to answer choice D. Okay, for number 22, I want us to figure out at equilibrium, or which has the greatest equilibrium concentration, or constant. And so we have a bunch of redox reactions. And we can relate KEQ to our standard cell potential. And so we know if we increase our standard cell potential, we'll increase our KEQ. And so we just want to figure out what our standard cell potential is, and whichever is the biggest will have the biggest KEQ. So we'll go ahead and figure that out for each equation. So in this top one, we have the reduction of copper, which has a potential of 0.337 volts. And we have the oxidation of zinc, which has a potential of 0.763 volts. So we can add those together and we get a cell potential of 1.1 volts. And we'll just do that same thing for each one. So for B, we'll have a cell potential of 0.614 volts. and for C we'll have a potential of 1.67 volts. For D we'll have negative 0.4 volts, and for E, negative 0.811 volts. And so we want the greatest standard cell potential to get the greatest KEQ, and so the answer here will be C. In number 23, Brooke is building a galvanic cell with a cobalt electrode immersed in cobalt nitrate, and then she has a manganese electrode immersed in manganese chloride. So we want to figure out which is produced at the anode, so we just want to figure out which of these two is going to be oxidized. So here I've written the reduction reactions for both of them, and we can use the table to get these values. And we can see whichever one is more positive is going to be the one that's reduced. So the reduction potential for cobalt ions is negative 0.277 volts, whereas the reduction potential for manganese ions is negative 1.18 volts. So the cobalt is going to be at the cathode being reduced, and the manganese compartment would be the anode. And the reaction that would actually be happening would be the manganese solid losing 2 electrons to become manganese ions. So the thing that's produced at the anode are these manganese ions, which would be answer choice C. In number 24, we have another voltaic cell or galvanic cell. Voltaic, if you feel like mixing those two words. And we're trying to figure out the maximum amount of work that can be done by the cell. And so whenever I see work, I think I'm looking for delta G, which is like kilojoules. So when I look at the solutions that I have some silver and some nickel, and I'm not working at 1 molar, so I'm not at standard conditions, and we'll have to use this full equation. So to start, I'm going to figure out which side is the anode, which is the cathode. So here I have the reduction reactions written for both, and I'm going to look at the potentials for the reductions and see which one is more positive, and that will be the side that's being reduced. So I have both the reduction potentials written here, and I can see that the silver side is more positive, so that reduction is going to be more favored, and I'll have to oxidize instead the nickel solid to make nickel ions, and that will serve as our anode. So when I flip that reaction, I flip the sign on the half reaction potential. And now I can add those two potentials together to get my standard cell potential, which is going to be positive 1.079 volts. And I want to add these two reactions together to get my overall equation. But when I add them, I need the electrons to cancel, and right now that's not going to happen. So I can multiply my top reaction by 2 so that the electrons cancel, and then I can add my reactions together. We'll have 2 silver ions reacting with nickel solid to make 2 silver metals and a nickel ion. And there were 2 electrons exchanged in this process, so my N is going to be equal to 2. Okay, so now we have a lot of the stuff that we need for this equation, but we still need to figure out what Q is given these concentrations. And so I know from my overall reaction that Q is going to be equal to my concentration of nickel ions that are aqueous divided by my concentration of aqueous silver ions squared. So we'll have 0.0155 divided by 2.5 times 10 to the minus 4th squared. And we end up with a Q of 2.48 times 10 to the 5th. So now we have everything we need to plug into this equation. We can get our non-standard potential by taking our standard cell potential and subtracting off this term to adjust for not being at standard conditions. And our non-standard potential is 0.919 volts. And so now once we have that, we can use our delta G equals negative NFE equation to solve for work. And when we do this, the number will pop out in joules, so we'll have to do an easy kilojoules conversion. So delta G is going to be equal to negative N, which is 2, times F, which is Faraday's constant, which is on the data sheet. And that's in coulombs per mole, times our potential, which is 0.919 volts. And this number pops out as negative 177,402 joules, which I'll say is the same as 177 kilojoules. Okay, so the correct answer here is D. Okay, for number 25, we're doing electrolysis, so we have a non-spontaneous reaction that we're forcing to occur, and we have aqueous nickel bromide. So I've written out here the nickel ions in water, the bromide ions in water, and we'll say that these have the potential to be reduced, and these have the potential to be oxidized. Okay, and so we can write the nickel reaction. So you can think of nickel as gaining 2 electrons to form solid nickel. And this has a potential of negative 0.28 volts. And when we think about the reduction of water, we think of it as 2 waters gaining 2 electrons to form hydrogen gas and some hydroxide. And this has a potential of negative 0.83 volts. Okay, and so we'd say that at the cathode, we would form nickel solid because this reaction is the most positive. So that would happen at the cathode. But we don't care about the cathode, right? This question's asking us about the anode. So let's go ahead and look at what could be oxidized. So we have the bromide, and we can think of 2 bromides becoming Br2 liquid, losing 2 electrons with a potential of negative 1.065 volts. And then we have the oxidation of water, which is 2 waters, losing 4 electrons to generate oxygen, gas, and some protons. This has a potential of negative 1.23 volts. So we want to pick which of the oxidation reactions has the most positive potential, which will be this bromine reaction. And so this is what will happen at the anode. And the product of that is the bromine liquid. So the answer here is C. Okay, so that's it for practice exam 4S. So make sure you keep working and stay in charge of the material, and you can do it, okay? Be sure you're practicing the problems and using your calculator that you'll have for the exam, and you guys will do great. Hang in there.